So as you see, my title is Reverse Mathematics over a Weak-Base Theory, and I will explain very briefly what that is on the first slide in a moment, and then give you more details as the talk progresses. But I've been told that reverse mathematics is not something that most people in the audience will know, especially the students in the audience are likely to not know the area. So I will spend a large part of my talk, more than 1/3 of my slides are a gentle introduction, hopefully gentle, to this area to give you some idea of what it is about. From the point of view of somebody who is not really an expert. So Young was kind enough to say that I'm an expert in reverse mathematics. I have done some work in it, but my perspective in the area is different. Most people working in the area come from computability theory and know much more about it, much more about it than I do. My background is more in models of arithmetic, proof complexities to some extent. So I'm kind of an outsider. So this will be a slight outsider's perspective on the area. So let me start then. Reverse mathematics is a program in mathematical logic. It's now around a half century old. It got started in the early 1970s by Harvey Friedman with a talk at the International Congress of Mathematicians, although you could say it got started earlier. So the idea is that you want to study the strength of axioms, the logical strength that one needs to prove theorems of mathematics. So like the inherent logical strength of mathematical theorems. And you could see like early signs of this sort of area being studied when people proved various theorems or various statements in mathematics to be equivalent to the axiom of choice, for example, in set theory. But eventually, this name, reverse mathematics, got attached to a more specific program, namely, people study the strength of mostly relatively basic mathematical theorems, often the kind that you would encounter in your first couple or 3 years of undergraduate studies at a university, though not only such theorems. Many of them are supposed to not be very highly set theoretic. They're supposed to be ordinary mathematics. And the way you study them is you formalize them in the language of an axiomatic theory called second order arithmetic. And then you prove equivalences between these theorems or implications between these theorems and some set existence principles which measure their logical strength expressed in this language of second order arithmetic. And of course, to prove an equivalence, you need some basic axioms that will make sense of the theorem and the set existence principle. You need some weak theory in which you prove the equivalences. And with this, weak theory is called a base theory. I will also maybe mention that this idea of reverse mathematics, it doesn't have to be tied exclusively to the setting of second order arithmetic. So as I mentioned, various investigations of the strength of more harder, logically harder statements within set theory, that is also within this idea. People also study third and higher order reverse mathematics. Sam Sanders, who's in the audience, is an expert in that. On the other hand, much lower, I've recently, for example, seen a paper, and it's not the first one of the kind, in reverse mathematics of computational complexity lower bounds, where the theories studied are within bounded arithmetic, which is much weaker than second order arithmetic. But usually reverse mathematics is this program of studying, refers to this program of studying the strength of statements as formalized in second order arithmetic. Many of the theorems that people study in this way, they analyze, are pi 1, 2. What this means is that they say that they are of the following form. For every x, which is a subset of the natural numbers, there is a y, which is also a subset. It's a set of natural numbers. and that there's some relation between x and y that no longer quantifies over sets of natural numbers, but just only over natural numbers. As common in logic and the foundations of mathematics, these sets of natural numbers may also code various other objects. For example, a real number can be represented as a set of natural numbers. A continuous function on the reals can be represented as a set of natural numbers, and so on. The more complicated the object, the more delicate these codings are, but I will try to avoid these issues to the extent that I can. But anyway, many of these statements are pi1, 2, so they have the form, for every set of naturals, there exists a set of naturals, y, and then something that doesn't quantify over sets of naturals anymore, just over natural numbers, so over finite objects. And very often, the strength of axioms that you need to prove for every x exists y is related to how complicated it is to compute y given x, how complicated in the sense of computability theory. So, for example, can y be computable with x as oracle? Does y always have to compute the Turing jump of x? Can y be low in x, and so on? And therefore, the field has a very computability theoretic flavor. I will mention it sometimes, but this will not be as emphasized as it would be in a typical talk about reverse mathematics, because firstly, it's not really my area of expertise. And secondly, the kind of flavor of reverse mathematics that will be happening here is somewhat less computability theoretic, at least at times, than the usual kind. So in this talk, eventually, when I get to like the research part of this talk, the more recent work, I will focus on what happens if we make the base theory, this theory that you use to prove equivalences between mathematical theorems and, say, set existence axioms, when you make it weaker than usual. But that will come only in, I would say, the second half of the talk. The first one will be like a very general introduction. So this language of second order arithmetic, it comes with two sorts of variables, which are called first order and second order. So the first order variables are those that you might know from piano arithmetic, for example, or generally first order arithmetic. We'll use lowercase letters, either like X, Y, Z from the end of the alphabet, or things like A, I, J, K, N, that would stand for, that you think of associated with integers. And the intended meaning of these variables is that they denote natural numbers. So for the first order sorted variables is for first order objects are natural numbers. And as usual in logic, you can use natural numbers by standard coding tricks to code finite sequences of natural numbers, to code rational numbers, and so on. So any kind of reasonable finite objects can be represented by the first order sort. And the second order sort, we use capital letters for that, say X, Y, Z capital, is intended to stand for subsets of the natural numbers. So the second order variables, the second order objects are sets of natural numbers. And a set of natural numbers is essentially countably many bits, so it's a countable amount of information. And therefore, the second order objects can be used to code things that we use countable amounts of information, like real numbers, for example, or like infinite sequences of natural numbers or of rational numbers, and so on. The extra logical symbols that we have in this language are, firstly, on objects of the first order sort, we have the usual arithmetic. So it's the language of ordered rings. Say we have plus and times, we have ordering, and let's say that we have constants for 0, 1, 1, just to make things elegant. And there's also a membership relation between a first and a second order object. So a number can belong to a set, or not, depending, of course, on the number in the set. There are some typical quantifier hierarchies which are which are used to measure the complexity of formulas and definitions in this language. So I will mention them. I expect that many of you are familiar with them, but just to be clear on this. So sigma 0n is the class of formulas where we have n blocks of first order quantifiers, so just over quantifying just over first order variables, starting with an existential block. So sigma 03 would be exists a number, for all numbers exists a number. And then after that, you can only have bounded quantifiers. So you may still quantify, but it's about the quantifiers after these n blocks have to quantify over numbers that are bounded by some sort of term that also describes a number. The dual class pi 0n is, again, n quantifier blocks, but they start with the universal blocks. So pi 03 would be for all numbers exists a number for all numbers. So the definition of a limit, for example, of a sequence can be stated in a pi 03 way. And as an example, I want to emphasize this at least a little bit, this connection to computability, because it will be needed at some point. Any computably enumerable, or if you prefer recursively enumerable, subset of the natural numbers can be defined by a sigma 01 formula. You say that there exists a computation that terminates and says yes, it accepts a given input. This famous P does not equal NP conjecture is a pi 02 statement. P not equal to NP says that this Boolean satisfiability problem, which is an NP complete problem, is not in polynomial time, not in deterministic polynomial time. So to express this, you say for every polynomial time clocked Turing machine, that can be represented by a number. So it's a number quantifier. It's for all Turing machines that attempt to compute SAT. There is an input on which the machine gives the incorrect answer. So that's the existential quantifier. So for all exists, that's pi 2. The twin prime conjecture of number theory is pi 2, and quite a few other mathematical statements can be formulated. This may be, if you're not used to this, it may be surprising how expressive this language is. Many things can be stated in like a pi 01, pi 02, or pi 03 way, even if they look to be referring to much more complicated mathematical objects. We will work a little bit with the lowest level of the quantifier alternation hierarchy of second order quantifiers as well. So the classes sigma 1n and pi 1n many alternations of second order quantifiers you have. So, and you ignore first order quantifiers. For example, pi 1 is the class of formulas that say for all sets, that's the universal quantifier on a second order variable. For all sets, something happens, and that something happens can be, like sigma 055, for example. It can use as many first order quantifiers as you want. That's not counted towards this index here. So yeah, that is the basic setup. I don't know if you can ask questions, if there is a way for the audience to ask questions along the way, by the way, but at least the people who are here on Zoom, if I say something that sounds strange or that seems to require a comment or a question, please do use the opportunity and ask me along the way. So full second order arithmetic, that's a theory called Z2, where I think Z is from the German Zahl for number. This is a theory in the language that I just described a moment ago with the first order and second order variables. That has the following axioms. Firstly, it has just it's a finite list of axioms that tell you that the first objects form the non-negative half of a discrete ordered ring. So there are things like, addition is commutative, and associative, and similarly for multiplication. The ordering is actually linear ordering, and it agrees with the operations in the usual way, right? If you add a number to an inequality, the inequality is preserved, and so on. Element, and there is nothing between k and k plus 1. K plus 1 is the next element after k. And that sort of axioms. These are like very, very basic things, just to make sure that we're working in the kind of structure that we may care about. Then there is this axiom that gives or the combination. There are the two axioms that give the power to this theory. So firstly, we have the comprehension scheme. We have this for all formulas of this language. So for any formula, well, it should not have x as a free variable, but for essentially any formula phi that can have parameters, so there are some implicitly universally quantified parameters here, we say that there exists an x such that for every number k belongs to x exactly if it has the property described by formula phi. So any formula in this language corresponds, there should be a k, sorry, if that's a typo, let me use the annotation device every now and then. So this should be a k. I'm just using the zoom thing, so I will erase it once we get to the next slide, but I hope you see what I mean. And so, every property that you can express corresponds to a set of natural numbers, and sets of natural numbers, therefore all definable properties or expressible properties, satisfy the induction principle. So we have an induction axiom saying that for every x, if it contains 0 and is closed under taking successor, taking +1 of a number, then it contains all numbers. So that's the usual mathematical induction principle. So the intended model is omega, meaning the standard model of piano arithmetic, with as the first order part of the model, and the power set of omega as the second order part. So like omega is the intended model of first order piano arithmetic. This theory has omega and the power set of omega as its intended model. Okay, let's see how I always forget how one could move once you do the annotation. I just dropped the annotation. Okay. I have to erase this thing because I will keep going. Next slide. Okay, so this theory, Z2, is extremely strong from the point of view that we want to do. Not every reasonable mathematical statement is expressible in the language of second-order arithmetic, but once a statement is expressible, if it resembles some kind of reasonable mathematical theorem, it is like almost always provable. I mean, I could give exceptions to this rule, but that's because I'm a logician. But something that a typical mathematician would think of, if you express it in this language in some way, which takes some coding and some getting used to, it's almost always going to be provable. In a sense that they will not make precise, but you could make it precise. It basically says that the two theories prove the exact same class of theorems of a certain complexity. Z2 is something like countable set theory. So it's Zermelo-Fraenkel set theory without the power set axiom, and including an additional axiom that says every set is countable. So from the point of view of, say, undergraduate calculus, this is an immensely strong theory. It's much too strong, in fact. So if we
Excuse me, please. May I just clarify? I would like just to clarify. So, did you say that it is Zermelo-Fraenkel without power set, but with additional axiom, every set is countable? Do I understand correctly?
That's right.
Because
yes.
Because here you can put parentheses in two ways and not clear.
I see. Yes. So maybe I will not draw parentheses because each drawing I make then has to be erased.
Thank you. I just would like to clarify.
Sure. Yes, this is, we drop the power set axiom and we add an axiom that contradicts the power set axioms. Namely, we say that every set is countable or finite. So we just ignore. This is a theory that ignores uncountable sets, although sometimes it can refer to them in an oblique way, right? It will not have a set of reals, but it will be able to talk about individual real numbers. It will also be able to say for every real something happens, and so on. So this is like the limit theory. This is like true arithmetic in some sense, and in the typical kind of reverse mathematics that people do, one has to study weaker fragments of. Example of what a weaker fragment means. Consider this theory
Excuse me, please. Once again, back to the previous slide. Could you please? Still, every set is at most countable, I believe.
Yes, so countable can mean countable infinite, or it can mean has an injection to the integers. And I mean the second meaning, yes.
Thank you once.
Yeah, sure. So let me give you an example of a weaker fragment of Z2 that is actually useful in reverse mathematics. I will sketch an example of how it appears. This theory called ACA0 for arithmetical comprehension axiom. The first A stands for arithmetical. Differs in the following way from Z2. It only allows comprehension for properties that are arithmetical, where arithmetical means expressible by a formula that does not have second order quantifiers. So you're only allowed to quantify over natural numbers, or maybe over rationals or some other objects that can be coded as rational numbers. So every arithmetical formula is, up to logical equivalence sigma 0n or pi 0n for some number n. So to illustrate how this differs from Z2, here's an example. So let's say that you already have some sort of partial order. You already have some set of natural numbers. Of course, you can think of pairs of natural numbers as well. So a binary relation on naturals can be represented by a set of naturals. And let's say that you know that this is a partial order. And then you might want to consider the set of those elements of this order such that there are infinitely many other elements below them. And this set you will have access to in AC0, because this is, so how do you say that there are infinitely many L that are below K? Well, you say that for every natural number n, there is an L greater than K in the usual number, greater than n in the usual natural number ordering. So this is not the non-curly, this is the usual ordering of natural numbers, such that L is below K in the curly ordering. So yeah, this is given access to the ordering of the natural numbers, which we always do because it's in the non-logical part of the language. This is how you say there are infinitely many L below K in this curly ordering. On the other hand, if you wanted to say that below K there is an infinite decreasing sequence, this you cannot have access to in AC0. You can talk about it, but you will not have a set of those K. Okay, so this set exists, it's guaranteed to exist, but this set would have to be the set of those Ks such that there exists a sequence, say Ln, indexed by natural numbers, such that something, something, something. And this sequence, this is a second order object. And well, if you know a little bit of descriptive set theory, you know that being ill-founded, an ill-founded order is a sigma 1,1 complete property. So that means that there's no way to express this in a purely arithmetical manner. So not quantifying about second order objects. But even if you don't know this, it's enough that you see that, well, you have to, that the usual way of saying there exists an infinite sequence of numbers below K in this special order, this curly order, you have to, the usual way involves a second order existential quantifier. So this is not an arithmetical property. So, such subtle differences will appear. And this theory, I will want to emphasize, because that is a large part of my interest in reverse mathematics. I care a lot about what these two-sorted second order theories, what they prove just about the natural numbers, the first order sort. So there is an easy model theoretic argument that I will not do here, but it's a relatively simple exercise for those of you who know a little bit of, say, model theory of arithmetic, that this theory is actually conservative over Peano arithmetic. So the theorems that it proves in the purely first order arithmetical language with no second order variables at all are exactly those that Peano arithmetic proves. Okay, so I erase this and we go on. So that was an example. ACA0 is one of the theories that people study in reverse mathematics, but we need to talk about the base theory. So the usual base theory is called RCA0, where RC stands for recursive comprehension, and recursive means computable. So this theory weakens the comprehension axiom further. It says the comprehension axiom that RC0 has is only delta 01 comprehension. The delta 01 property is one that is both sigma and pi 01. So this axiom says that if some property is expressible both by a sigma 1 formula and a pi 1 formula, then it determines a set. So we say that, given two sigma 1 formulas, or given a pi 1 and a sigma 1 formula, if they are equivalent, then they define a set, then they correspond to a set. Maybe I'll already highlight this connection to computability. As you may know, delta 01 definability corresponds to computability. So this theory, this comprehension axiom, in some sense corresponds to computable mathematics. If we have a property of natural numbers that is computable, meaning delta 01, possibly it is computable with oracle calls, so with questions about some things that we already know that are sets, say x1 up to xn. So if something is computable relative to things that we already know that are sets, then that property is also a set, that also corresponds to a set. So we're only guaranteed to have the computable sets as real sets, real second-order objects in this theory. Now, there's a slight surprise, maybe we'll see why this is helpful, but there's a slight surprise. This will actually be a matter of emphasis in the second part of the talk, concerning what kind of induction axiom you have. So if we just took the previous induction axiom, the same one that we had in full second-order arithmetic and in arithmetical comprehension, that says for every set, mathematical induction holds for that set, we only know that delta 1 properties are sets. So that would only give induction for delta 1 definable properties of natural numbers. And for some important technical reasons, that makes life difficult. That makes the theory maybe weaker than we would like it to. So we allow induction for sigma 01 definable properties. More properties have induction than those that correspond to a set. So only computable properties are guaranteed to correspond to a set of natural numbers, but sigma 1, meaning computably enumerable properties, are always guaranteed to satisfy the mathematical induction principle. A typical model, this is actually the smallest model in the set of containment of RC0, is, well, the standard model of first-order arithmetic as the first-order part, and then just the family of computable sets as a second-order universe. So this structure, which only sees the computable sets, is already enough to satisfy RC0, and this is the usual theory used as a base theory for reverse mathematics. In terms of first-order consequences, Young told me that most of the audience, in particular the students, will know the basic fragments of piano arithmetic. So this theory proves exactly those statements that sigma 1 induction, that I sigma 1 proves in the language of just first-order variables. So I wanted to do a very basic example of reverse mathematics, allowing for some things swept under the rug, and possibly there are some small gaps or like not quite precise statements in this proof. So I wanted you to consider a very basic fact from mathematical analysis. If you ever took a first-year analysis course, you must have encountered the statement that's known as Bolzano-Weierstrass theorem, at least in say the English-speaking mathematical world, but we call it the same in Poland as well, in translation, of course. And this is like the following basic property of real numbers, that any bounded sequence of real numbers must have a convergent subsequence. So let's even take a weak version of this. Let's say BW, Bolzano-Weierstrass. This weaker version turns out to capture the entire logical complexity of this statement. Let it say that any sequence, even of rationals, and let's say it's contained in the closed interval from 0 to 1. So any sequence of rationals between 0 and 1 must have a convergent subsequence. And a very basic theorem of early stage reverse mathematics is that over our base theory of computable comprehension, RC0, this is equivalent to arithmetical comprehension. And I will try to give you a flavor of how you prove this sort of thing, while avoiding as much as I can issues related to how exactly you represent a natural number, a real number as a set of natural numbers, and so on. I will try to abstract from that. So first, how do you prove Bolzano-Weierstrass in arithmetical comprehension? So we're given some sequence of rationals. It's bounded between 0 and 1. And we need to find a convergent subsequence. So the main thing about it, a convergent subsequence is one that has a limit, and this limit may be a real number. It might not necessarily be rational, right? It's not guaranteed that any subsequence of a sequence of rationals will converge to a rational number. The number might really be irrational. This is an important aspect of the completeness of real numbers that rationals don't have. So, as I said, I don't want to say exactly how real numbers
Excuse me,
are.
please. Could you please
Yes.
go back to the previous slide once again?
Yes.
Well, again, question: how do I understand convergence in Cauchy sense, or to have a limit? In Cauchy sense, it
no,
is
I
just
need to have a limit. So the statement says that there is a subsequence and there is a limit of it.
the limit. So not in Cauchy sense. So you assume completeness. You consume completeness.
Yeah, because that's the point. You can have for example, if you just had the rationals, you could have a
thank you. I just would like to clarify.
So this statement, that's a good point. This statement definitely contains a quantifier over the existence of a limit, and that's very important. So it's actually the heart of the matter. So really to say that there will be convergent subsequence comes down to saying that there is a subsequence that has a limit, and we're really quantifying over this existence of the R. And what we really need is to prove that there is this real number R that is the limit of a subsequence. And in order to be able to claim that a given real number exists, basically what you need is to have some sort of procedure, like an algorithm, that given n sort of computes the nth digit after the decimal point in the binary notation for that number. So we need some sort of procedure that on input n approximates this real number to within 2 to the minus n. This procedure, it does not have to be like a pure algorithm, because there might be some real numbers that will not be computable, and in that sense there might not exist such a procedure. The point is that it will be a procedure that can ask about membership of various things that we know to be sets, and this is what it comes down to. So consider the following set of pairs of natural numbers, but these can be coded as natural numbers, of course. So let the set X consist of those pairs KL, where these are naturals, such that K is smaller than L, and infinitely many of for infinitely many elements of our sequence, those elements are between K over L and K plus 1 over L. So we put the pair KL, the KL, which you think of as a sort of natural number, K over L, a rational number. We put it in the set if and only if there are infinitely many elements of our sequence of rationals that are between k over L and k plus 1 over L. And this set exists by arithmetical comprehension. As explained already, the property there are infinitely many elements such that something, something, something is an arithmetical property. You can express it using only quantification over natural numbers. So this is the important thing. We have the set. And now we need some sort of procedure. So we're given the set. We can ask questions about membership in the set. And now we need a procedure for approximating a limit, the real number limit of a subsequence of the sequence Q0, Q1. So we're given n, and we need to find a rational that will approximate this limit that we're looking for up to within 1 over 2 to the n. So given n, we look at the largest k such that the pair k 2 to the n belongs to the set X. So for example, let me draw something again. Let's say that k is 2. So we will split this interval from 0 up to 1 into 2 to the 2, meaning 4 pieces. So this is 1/4, this is 1/2, and this is 3/4. And let's say that, well, the points of this Qn sequence, well, they appear in various places. But let's say that after a while, no further points appear here above 3/4, but there are infinitely many between 2/4 and 3/4. So then this is going to be the largest number of the form k over 2 to the n. So 2 to the n is 4 in this example, such that there are infinitely many numbers above in our sequence above 2 to the n. K over 2 to the n. So there are infinitely many numbers in our sequence above 1/2, but not infinitely many above 3/4. So therefore, we say that a good approximation of our limit of a subsequence will be with up to within 1/4 will be 2/4, will be 1/2, because we will eventually find, by the usual argument, we will eventually find a subsequence of our sequence that tends to a limit somewhere within this interval. And then maybe if we have n equals 3, so between 2/4 and 3/4 there appears 5/8, for example. Maybe it turns out that there are still infinitely many elements above 5/8, so we will take as our approximation to within 1/8, we will take 5/8. And this sequence of approximations, 2/4 meaning 1/2, 5/8, and so on, it can be computed as long as you can ask questions: are there infinitely many elements of our sequence of rationals above this, the given rational? So we can use that. You can use the set X, which we know to exist, to be a set, to answer such questions. And therefore, once you have the sequence, you can check that it converges to a real number that the theory will recognize, and that's the limit of a certain subsequence of our sequence of rationals. So that's the kind of idea that you use to prove that there is this convergent subsequence, which comes down to the difficult thing is to prove that there exists a real that forms its limit. And that's half of the equivalence. Now I want to do the other half. So to do the actual reverse mathematics, let's prove a reversal, meaning let's now prove a set existence axiom from the Bolzano-Weierstrass theorem. So here's the other direction. So I will tell you how to prove, assuming that every bounded sequence of rationals has a convergent subsequence, I will tell you how to prove the comprehension axiom for sigma 0, 1 formulas. So formulas that have one existential unbounded quantifier. This is actually enough. This is actually enough to get all of the arithmetical comprehension, because this formula is allowed to use both first and second order parameters. So I'm emphasizing these parameters here. Normally, I tend to ignore them in this presentation. So we will have a formula about numbers k that says there is an L such that delta KL, delta is just a bounded property, it's in particular computable, but exists L delta KL, it might have other parameters, for example, a set parameter A. So once we know that every sigma 01 set exists, then we can also apply this to know that the universe of sets is closed under complementation. The complement of a set is definable in a very simple way, given a set. So we also get all pi 01 definable sets. And then once you put a pi 01 definable set here as your set parameter, you can get comprehension for sigma 2 formulas, and so on and so on. So the sigma 01 case is the crucial case. So let's do it. So we want to obtain the existence of the set of those cases that exists L satisfying the property delta with respect to k. So consider the following monotone sequence of rational numbers. It's like a very simple, it's going to be clearly bounded between 0 and 1, sequence of rationals. For convenience, let me start the numbering, the indexing of the sequence from 1 rather than from 0. And let's say that the nth number in the sequence of rationals is obtained as follows. In binary notation, it will always have 0 before the decimal point, and after the decimal point, it will have at most n digits. So anything beyond the nth digits will definitely be a 0. And we want to make the kth digit in binary notation, the kth digit after the decimal point, we want to make it 1 exactly if we already found confirmation, we found a witness to the property that there exists an L such that delta KL by looking at the first n numbers. So we look at the kth digit, and if we're computing the nth number in the sequence, so for example, let's try to compute Q2. So Q2 will definitely have a 0 here. It might have something or something here, and these things will definitely all be zeros. And let's say that, it's not true that delta of 0, I'm measuring it from, sorry, indexing from 1, fine. Let's say that not delta of 1, 1, but delta, and not delta of 1, 2, and not delta of 2, 1, but delta of 2, 2. Then, because looking at the first two possible L's, we did not find a witness to the property that there is an L such that delta 1L. Here, we put a 0. But because L equals 2 is a witness to the fact that there exists an L such that delta 2L, we put a 1 in the second position, and so on and so on. So this is going to be obviously a monotone increasing or non-decreasing sequence of rationals. We may only add new 1 bits as we go on in this computation. It is also clearly computable. We can, on input 10, we can clearly tell what the nth number is going to be, as long as we can make questions about membership in A, because then we only have to check, do brute force search over bounded domain by n to be able to tell what the bits of Qn R. So this is a sequence that we will have in recursive comprehension. And now Bolzano-Weierstrass tells us that some subsequence of this has a limit. Let's call this limit R. Then typical arguments, using monotonicity tells you that this limit of the subsequence must actually be the limit of the entire sequence. So that tells you that eventually there is this real that, you can look at, and it tells you can look at it and see whether, so this is the first, second, third, fourth, fifth, sixth, seventh bit, and you can eventually tell, by asking questions about this real, whether its seventh bit is one or not. And in that way, you can tell whether there is an L such that delta of 7L or not. So the set of those K for which there exists an L such as delta KL is exactly the set of those K such that the kth bit of our real number, of the limit of our sequence, is a 1. Since we have this real number, so we have a set of those K where the kth bit of the real number is 1, we conclude that we also have this set, which is what we're trying to prove. So this is how you prove in general the existence of like a general set existence principle from a statement about the existence of, well, real numbers that are limits to subsequences of say bounded rational subsequences of bounded sequences of rationals. So that's how you discover, say, logical strength or set theoretic strength in seemingly non-logical principles of undergraduate mathematics. Okay, so that concludes my sketch. And now I wanted to do a very, very brief and superficial, so let me apologize to all the experts in the audience. I wanted to do a very, very brief and superficial sketch of the history of reverse mathematics. I would say that there were two main stages of this history, although, of course, that's, as mentioned, a superficial explanation. So the first stage, starting with Friedman's initial work on reverse mathematics and then continuing through much of the 1970s and 1980s, although the state never completely concluded, people still prove results of this kind. What happened is that most of the theorems that were analyzed in this way turned out to be either provable in RCE0. So in some sense, you only need computable processes to witness them. The theorems were theorems of computable mathematics, or they were equivalent to one of 4 other theories that are actually linearly ordered in strength. There are 2 theories on this list that are stronger than ACE0, and I will not really talk about them here because our focus in this talk and my expertise is more in weak rather than in strong theories. Then going downwards in terms of strength, the third is the theory that I just described, arithmetical comprehension, ACE0. For example, it's equivalent to the Bolzano-Weierstrass principle. It's equivalent to Ramsey's theorem for triples, for exponent 3. If you don't, it's a combinatorial statement. If you don't know what that is, we'll have things to say about Ramsey's theorem, mostly for pairs, but not only, in a moment. So this will be coming up. It's also equivalent to Koenig's lemma, the statement that says every infinite, finitely branching tree has an infinite path. So many things are equivalent to ACE0, but it turns out that there's an important theory, 4th in order of decreasing strength, called WKL0 for weak Koenig's lemma, which is intermediate in strength between recursive comprehension and arithmetical comprehension. And it's a theory that says that every binary infinite tree has an infinite path or branch, where binary means we represent the tree as its nodes are sequences of zeros and ones only. So if there is a tree such that just from the look of it, we already know that it has to be finitely branching because every node may have at most two successors, itself extended by 0 and itself extended by 1, then that is guaranteed to have an infinite branch. And it turns out that this apparently subtle difference between arbitrary finitely branching trees and these like explicitly at most binary branching trees is a very important difference. It gives a weaker theory than ACE0. Weak Königs lemma is strictly weaker than a Königs lemma. And it's equivalent to many important theories, for example, in mathematical analysis. So, Bolzano-Weierstrass is one way of saying that the 0-1 unit interval is compact. This is called sequential compactness. Every sequence of reals within the 0-1 interval, closed 0-1 interval, has a sequence that's convergent to something in this closed 0-1 interval. Another way of expressing this is a different kind of compactness. This is covering compactness, Heine-Borel compactness. The compactness of the 0-1 interval, the closed 0-1 interval, is to say that if you cover it by, say, infinitely many, say, countably many open intervals, maybe with rational endpoints, then out of these infinitely many, you'll be able to select finitely many that already cover the entire interval. So that kind of compactness is equivalent to weak Königs lemma as opposed to Königs lemma. So it's weaker than ACE0. And it's also equivalent to lots of other basic analysis facts. Not only in analysis, but let me focus on analysis for concreteness. So for example, every continuous function on a closed bounded interval has a maximum and a minimum value. Every continuous function is uniformly on a bounded closed interval is uniformly continuous. Various important fixed point theorems and existence theorems, like Brouwer's fixed point theorem, Peano's existence theorem for differential equations, and so on. They all turn out to be equivalent to weak Königs lemma, so not provable in computable mathematics, but not requiring all of arithmetical comprehension. An important example equivalent to weak Königs lemma is compactness and completeness theorems for first-order logic. So both of these theorems, this is something that I would assume most of the audience will know. They're also provably in RC0 equivalent to weak Königs lemma. And this theory, WKL0, is, as mentioned, it's between RC0 and ACE0 in strength, but in some important senses, it's closer in strength to the weaker theory. So it's closer to RC0 than to ACE0. And the important sense is as follows. If you have a pi11 principle, pi11 statement, meaning for all sets and then just an arithmetical property. In particular, if you have purely arithmetical statement of just first order arithmetic, that is always pi11. And it is provable in WKL0, then it's provable over RC0 as well. We express this by saying that WKL0 is pi11 conservative over ACE0. So as a consequence, because the purely first order theorems of RC0 are exactly I sigma 1, the first order part of WKL0 is also I sigma 1. So that's much, much weaker than PA. So as you can see, even from the small list and from the examples that I mentioned, weak Königs lemma is much better at, allowing you to prove various basic facts of mathematics than just computable mathematics would be. But it turns out that in terms of its number theoretic consequences, the say first order arithmetic consequences, nothing changes. So this, this existence of this intermediate step that actually has no additional number theoretic consequences is a very important early discovery of reverse mathematics. Together, RC0 and these four theories above it that were equivalent to most of the theorems studied, they are known as the Big Five. And of course, already in the early going, there were examples of theorems which people could prove are not equivalent to any of these theories, but that was like the typical pattern observed. And then starting, well, this, as mentioned, I just mentioned this started earlier, but it became a more prominent phenomenon somewhere in the 1990s. People started discovering more and more exceptions to this big five pattern. Firstly, this is something that I will not go into this talk at all. Some theorems that were above AC0 but were not equivalent to either of these stronger theories that I mentioned previously that were part of the big five. And in some cases, they were provably strictly stronger than the strongest of those big five theories. So typical areas where such statements come from are, or theorems comes from, are theorems expressing, say, the determinacy of games with Borel winning conditions. Also statements about well quasi-orders. But as I mentioned, this is not the direction we're going in this talk. And second source of examples that evade this big five phenomenon is something that got called the reverse mathematics zoo. And there's actually a web page run by, I think, Damir Jafarov and one of his former students. You can eventually click on the link in these slides here that gives you diagrams describing what the zoo looks like. So the reverse mathematics zoo is a bunch of theorems that are intermediate in strength between computable comprehension and arithmetical comprehension. They are, most of the time, they're incomparable with Koenig's lemma. Very often, they're incomparable with each other. So if you look at these diagrams on this web page, eventually you'll see this sort of amazingly complicated web of implications and non-implications. So this neat picture of five linearly ordered theories to which everything is, or more or less everything is equivalent, got completely destroyed. And many theorems in the zoo are versions of Ramsey's theorem for pairs in two colors, RT22, which I will describe momentarily. So I will give you 4 examples of statements from the reverse mathematics zoo. That's why this slide is called one cage from the zoo. So it's just a very, very small, tiny slice of what is happening in this reverse mathematics zoo. Oddly enough, these 4 theorems will be linearly ordered in terms of strength. And I am listing them because I find them particularly natural and easy to understand for somebody who has not so much experience in this area. And they also turn out to be useful in analyzing many things in the zoo. And we studied them in a different context in a work of ours. I will come to that eventually, hopefully. So, as mentioned, a very prominent member of the reverse mathematics zoo, the first one that was really discovered, is Ramsey's theorem for two colors. So what it says is that if you have a function that takes unordered pairs of natural numbers and gives each pair a color of 0 or 1. So you can think of the complete graph on the natural numbers, or just complete graph on any infinite set, but we'll represent it as graphs on the natural numbers. That each color is colored either 0 or 1. It's colored blue or red. So then there's going to be an infinite subset of our set. So in this case, an infinite subset H of the naturals, such that on that infinite subset, the coloring is constant. So if you color, say, the natural numbers, this makes sense for any other infinite set, but let's focus on the naturals. If you color pairs of natural numbers, I mean unordered pairs, so edges between 2 points in an unordered infinite graph, undirected infinite graph, by 2 colors, then there will be an infinite subgraph on which the coloring is constant. So there is an infinite subset H of the naturals, such that on pairs from this set H, the coloring is either always 0, always 1. That sort of set is called a homogeneous set. So that's why I'm using the letter H. Now, for example, when we in Warsaw teach a basic set theory course and we introduce Ramsey's theorem and we want to give students some exercises that can be proved using Ramsey's theorem. So one exercise is as follows: that if you have an infinite partially ordered set, so we'll represent that as an arbitrary partial ordering on the naturals, then there's an infinite chain or infinite anti-chain. So there is an infinite subset of the domain of the partially ordered set. So there's an infinite subset H of the naturals, such that on the subset either all elements are comparable or no two elements are comparable. So it's either a chain or an anti-chain. Every infinite partial order contains an infinite chain or an infinite anti-chain. This is called the chain anti-chain principle. And it's an easy exercise for students that it follows from an application of Ramsey's theorem for pairs. And in reverse mathematics, it has its own name, the chain anti-chain principle. Another consequence of Ramsey's theorem for pairs is something that is the following fact: in any infinite linear ordering, again, we represent that as a linear ordering on the natural numbers as its domain, there is going to be either an infinite ascending sequence or an infinite descending sequence. So that's another basic thing that you can prove, well, in a number of ways, but in particular by applying Ramsey's theorem. That's called the ascending descending sequence principle, ADS. And the fourth principle that I want to mention is the following: for every coloring of pairs of naturals by two colors, there is an infinite set that we no longer require to be homogeneous. We no longer require that all edges between points in the set have the same color, but we require the following: that for any point in this color, in this set, only well, all but finitely many edges coming out of this point will have the same color. So for any point in this infinite set H, there is another point which we can assume to be in the set as well, so that for any point in the set larger than this point y in the natural number ordering, the edge between x and z and the edge between x and y will have the same color. So if you look at the set H and you look at some point in it, say x, and you look at the edges coming out of it to other points in H, there might be finitely many red edges, but eventually all edges will be blue. Or from another x prime, there might be finitely many blue edges, but eventually all will be red. So this is a weaker property than homogeneity. So it's like an obvious consequence of Ramsey's theorem for pairs. And in fact, these guys are linearly ordered. So provably in RC0, Ramsey for pairs implies the chain anti-chain principle, which implies the ascending descending sequence principle, which implies this last principle, which I forgot to mention. It's called CRT22 cohesive Ramsey's theorem. I won't explain why it's called cohesive, why that's the name, but that's what it's called. Of these implications, only the last one is kind of non-trivial, I would say. The implication from Ramsey to chain anti-chain and from chain anti-chain to ascending descending sequence, those are like easy student exercises. But the last one is tricky, and it actually involves some logical strength. Maybe there'll be time to mention that, but I'm not sure. So these things have been studied a lot. Lots and lots is known about them these days. Let me tell you, like in an extremely brief sketch, what kind of things are known. So, as mentioned, there are these four principles, these four Ramsey theoretic principles. They're linearly ordered in terms of logical strength over RC0. Each on the list implies the next one. None of these implications provably reverses in RC0. So no pair of 2 among these 4 statements is provably equivalent in RC0. So, for example, Ramsey is strictly stronger than the chain-anti-chain principle in terms of implications over RC0, and so on for other items in this list. All 4 of them are not comparable with Königs lemma. The most challenging result in this area was to prove that Ramsey for pairs does not prove weak Königs lemma. This was proved by Liu a little bit more than 10 years ago. As mentioned, my particular interest is first order strength. So RC0 plus Ramsey for pairs does not imply sigma 2 induction, but it implies the so-called sigma 2 bounding or sigma 2 collection principle. If you're not familiar with that, please just think of it as delta 02 induction. So a principle saying that if a sigma 2 and a pi 2 formula are equivalent, then you have induction for them. So the purely first order consequences of Ramsey are a proper subtheory of I sigma 2. And we also know that at least for pi 03 theorems, Ramsey for pairs is conservative over RC0. So we know that if you prove a pi 03 theorem provable from Ramsey for pairs, then it's actually provable without using Ramsey for pairs. We know that it's not true for pi 04, but we have a candidate theory for what the pi 11, what the first order consequences of Ramsey for pairs could be, but it's an open problem. It's actually a major open problem whether that is the correct set. So the first order consequences of Ramsey for pairs are not fully known. I should mention that, I'm trying to list the references, but not really state the authors. I should mention that this pi 03 conservativity result of Ramsey over recursive comprehension, which is a major breakthrough in the area, is from a paper co-authored by Keita Yokoyama, who is present here. It's a paper by Ludovic Bataille and Keita from a few years ago. For the weaker principles on this list, we know exactly what their first order consequences are. So the chain-anti-chain principle and the ascending-descending sequence principle, they prove exactly delta 2 induction or sigma 2 collection if you prefer, but nothing more. Their first order consequences are exactly B sigma 2 or I delta 2. That's a result due to Chong, Slayman, and Yang. And the weakest of the 4, cohesive Ramsey's theorem for pairs, is actually fully pi 11 conservative over our base theory. So the first order consequences are just I sigma 1. That's due to an important paper of Cholak, Jokush, and Slayman more than 20 years ago. So so this one is weakest also in terms of the first order consequences. Okay, and I think, let me see what the next slide is. Yes, I think that concludes my gentle introduction part. I have to stop here. I've already taken, it was just a bit more than 1/3 of my slides, but I've actually used almost 2/3 of my time. So the more advanced part of the talk I will go over it very slowly. But if you want to read more, if you want to get into the area, there are 2 very good monographs, each of them kind of complementing the other. There's this classical book by Stephen Simpson that emphasizes what I would say the logical aspects of this theory, Subsystems of Second Order Arithmetic. I think it's a great reference book. Maybe it's a little bit dry to read, but it's very useful to get an understanding of the field, and has a very nice introductory chapter that sort of sets the setting. It's old enough that it does not really describe this reverse mathematics zoo phenomenon. It's more about the big 5 and also various relationships between those theories and conservativity results, model theoretic properties, so that it has a very nice second half of the book devoted to such aspects that are not reverse mathematics in the strictest sense, but to me, they're as much or even more interesting than just proving equivalences to mathematical theorems. Then there's a much more recent book by Jafarov and Mummert called simply Reverse Mathematics. That one has a lot about the zoo. It's a more modern approach. It emphasizes the computability theoretic aspects, which I'm kind of de-emphasizing here, but they are really very important in the area, and they're given like their full due. They are given the prominence they deserve in this more recent book. There is another monograph by Dennis Hirschfeld called Slicing the Truth, which I think is also a very nice reference book, but that one is slightly more advanced, I think, in terms of background assumed. It's a few years earlier than Jafarov and Mummert, and it's slightly more limited in scope. So I've not put it up on this picture, even though it's one of my favorite books in the area. And there's actually a popular science book by John Stilwell called Reverse Mathematics. It's not a very long book. I think it's under 200 pages. I have to say that I'm a great fan of Stilwell's work in general. I've read at least 5 books of his. This one is not my favorite. Turns out that Reverse Mathematics is not so easy to popularize, but I think it's also useful and enjoyable reading. And as I said, it's not a long book, so it makes sense to get an idea of what the field is about by looking at this book at some point. And now we come to the proper topic of this talk, which is the weaker base theory. So as you remember, our base theory RC0 had delta 1 comprehension, meaning we know that every computable set, or every set that is computable using oracle questions to things that we already know to be sets, every computable property determines a set. But we had induction also for computably enumerable properties, for sigma 0, 1 properties. So now we drop that stronger induction axiom. Let's go back to the usual induction axiom. So every set that contains 0 and is closed under successor contains all numbers. So because our comprehension axiom only tells us that computable properties will have to correspond to sets, the others we don't know, we are only guaranteed induction for computable properties. Therefore, this decreases the strength of induction in a significant way. And it turns out, for example, that the axiom that says, or the statement that says a given number k, for a given number k, 2 to the k exists. You actually need this existential quantifier. There exists a number that equals 2 to the k for that. And if you drop sigma 0, 1 induction in favor of this basic induction axiom, you can no longer prove it. You can no longer prove that for every k there exists a number that is 2 to the k. That's the exponential of k. And for that reason, because this exponential function is extremely useful in applications, it basically tells you that you can represent a finite set by the string of bits of a number. So that finite sets correspond to first order objects. We add it as a separate axiom. So there's a very important star missing here. So this theory, which is called RC0 star, I don't think it's a very convenient name, but that's how it got called, and it has to stay called that way. This allows the sigma 1 induction axiom. We only have the basic induction axiom, which gives us induction for delta 1 properties. And we explicitly say that every number has an exponential. And this theory, RC0 star, sorry, I missed the star here. That's an unpleasant typo. In terms of first order consequences, it's equivalent to delta 1 induction, or sigma 1 collection, if you are used to that, plus this axiom saying that exponentials exist, that the exponential function is total. Okay. So it's a weaker, it's proof theoretically weaker than RC0. For example, it will not prove that the iterated exponential function, the so-called tower function, n goes to a stack of 2 to the 2 to the 2 to the 2 n times. This theory, RC0 star, please remember about this missing star here, will not be able to prove that. So now let me explain what really happens if you drop sigma 1 induction. So what does the failure of sigma 1 induction? So apparently this part of the talk has an increased density of typos. So what does the failure of sigma 1 induction mean? So assume that you have a model consisting of a first order part that you think of as numbers and a second order part that you think of as sets, and of our weaker base theory, RC0 star, and assume that it is not a model of RC0. So some instance of the mathematical induction principle for sigma 1 formula fails. Now it turns out that it means that the following will always happen. Firstly, in this model, there will be a sigma 1 definable proper cut. We'll call this cut J. So a cut is something that's called contains 0 and is closed under successor. So failure of sigma 1 induction means that there is an initial segment closed under successor that's not the whole model, but is sigma 1 defined. And secondly, there is a set in the second order universe that's called the set A. So there's like a legitimate second order object, which is infinite in the sense of being unbounded in the numbers. So there are arbitrarily high elements of this set, but which in some sense has a lower cardinality than the set of natural numbers. So if you enumerate the elements of this set in an increasing way, you index them as A0, A1, A2, and so on, then this enumeration only uses indices from this cut J. So we can say in some sense that the cardinality of the set is not, it's an unbounded subset of the natural numbers, but the cardinality of the set is no longer the set of all natural numbers. There is no longer any bijection between the set and the set of natural numbers. But the cardinality of the set is in some sense this cut J. So in RC0 star with negated RC0, so in a model where we don't have sigma 1 induction, there will always be this, so to speak, very, very sparse, like very, very not dense, unbounded set, which for some natural number k, well, a number above this cut J, so we could put k here, for example. For some natural number k, this unbounded set will not contain, or infinite set will not contain a k element subset. Because if you enumerate the elements of this unbounded set, the enumeration only goes up to this proper cut J. So in some sense, if you know basic cardinal arithmetic from set theory, what happens once you drop sigma 1 induction, this is an observation that was made like in the early stage of research in this area, in some sense, the cardinality of the set of natural numbers behaves like a singular cardinal. There is this unbounded subsequence of the natural numbers whose cardinality is smaller than the set of all natural numbers. So that's like a very strange phenomenon, and you have to get used to it. Once you're working in this setting, and this has a number of weird and interesting consequences. So let me give you a basic example of reverse mathematics over this weaker base theory. This example comes from the very first paper that introduced this weaker base theory, this star theory, namely a paper by Steve Simpson and Rick Smith from the mid-1980s. So they proved the following. I will not sketch a proof this time. This is just an example of a result. That over this weaker base theory, RC0 star, sigma 1 induction, meaning RC0, the stronger base theory, is equivalent to the following very basic statement of algebra. For every countable field, okay, and every non-zero polynomial over that field, the polynomial has only finitely many roots in the field. So the statement that non-zero polynomials have finitely many roots is actually equivalent to sigma 0, 1 induction. It's equivalent to the stronger base theory over the weaker one. And if you look at the proof, of the interesting implication that polynomials have finitely many roots, that already implies the sigma 1 induction principle, you see that once you're given a violation of the sigma 1 induction principle, so once you're given this very sparse infinite set that only has cardinality, a proper cut of the natural numbers, as opposed to the entire natural numbers, you can construct a polynomial over an appropriate field. That's also a part of the construction, which will have the degree of this polynomial will be somewhere here above this cut J. And in a loose sense, well, again, you could make it precise if needed. It will only have this many roots. The number of its roots will actually be this cut J. So it makes sense. The number of roots is actually smaller than the degree of the polynomial, because the degree of the polynomial is somewhere here. But the set of those roots is somehow so distributed that it's infinite as a subset of the field coded within the natural numbers. So the set of the roots of that polynomial is exactly this kind of sparse infinite set. So I looked at this seminal, this initial Simpson-Smith paper from 1986 in Scopus, the Scopus bibliographic database when preparing this talk. And it turns out that it has like almost 40 citations. I think the number is 39, if I believe, but only like 6 or 7 are from the 20th century. So the remaining 30 plus come from the 21st century. So it's not an extremely hot topic, but it's a topic that attracts significant interest now. But the interest is somewhat recent. It got going in the last 2 decades or a bit more, rather than in, say, the first 10 or 15 years after the publication. So at the turn of the century, there was a volume of papers about computability theory published in the year 2000, and that contains a sort of survey on open problems and more general questions in reverse mathematics by Harvey Friedman and Stephen Simpson, so 2 important developers of the field. And one of the issues they mentioned as worth studying, like a group of research projects worth studying, concerned this weaker base theory. So one topic they propose is to redo all of reverse mathematics using this weaker base theory. They say that the groundwork for this has been done, but there are some difficulties. For example, Ramsey's theorem for exponent 3, meaning for triples, is equivalent to arithmetical comprehension over RC0, but it is unclear. I was copying this, so maybe there's a typo in the paper itself, but I'd have to check. Maybe something got lost in the copying. But it is unclear whether you can weaker RC0 to RC0 star in this implication from this equivalence between Ramsey's theorem for colorings of triples and arithmetical comprehension. So one idea they had is like, try to redo as much of reverse mathematics as you can using the weaker base theory. Another project was to find mathematical theorems that really need the sigma 1 induction. So let's track uses of sigma 1 induction in mathematics. So let's look for theorems that are equivalent to RC0 over RC0 star, like this theorem about polynomials that I mentioned previously. Several results of this kind are already known. And here they refer to, for example, the paper that I listed that has some examples from algebra. For example, the PhD thesis of Kostas Hatzikyriakou from the late 1980s, which had further examples from algebra, and a few others, but not so many, in fact. And this sort of got going, especially in the last, say, quarter century. The ideas that Simpson and Friedman suggested, they were developed to some extent. So if you look at this list of papers citing the Simpson-Smith paper, there is a non-trivial number of papers with a relatively wide diversity of authors. So it's not just one person, but it's a number of independent groups where people actually make the effort to show that a certain reverse mathematics equivalence holds over RC0 star. So maybe they're not redoing the old results, but they're often proving new results and checking that you only need the weaker base theory to prove the equivalences or the implications. And I would really single out any specific paper here. There's more than one, and it's a wide variety of topics. So let me maybe not give an example of this. Then there are also these papers that show that various theorems are equivalent to sigma 1 induction over RC0 star. So in some sense, they fulfill the second suggested project from the Friedman-Simpson survey. They track necessary use of sigma 1 induction in mathematics. So for example, Simpson himself proved that one way of stating the bare category theorem, actually probably most reasonable ways of stating the bare category theorem, they really require sigma 1 induction. And there are other examples also by other people where this turns out to be necessary. Something that also got going pretty early, although it's not explicitly in the language of RC0, it's usually done in a purely first order setting. So it's an I delta 1 plus exp. It's especially been developed by the Singapore school. So C.T. Chong, Yue Yang, they had this collaborator Morad in the 1990s. This project was called reverse recursion theory. So their aim is to identify how much induction strength, in particular whether you need sigma 1 induction or not, is needed to prove various classical theorems of computability theory. So for example, one very nice result from Chong and Morad in the early 1990s was that our weaker base theory, RC0 star, proves the Friedberg-Muchnik theorem, the existence of incomparable recursively enumerable degrees. But they have other results saying that for other classical theorems of computability theory, you will need sigma 1 or maybe even sigma 2 induction, that they're actually equivalent to those cases of induction. There's a question on the chat. Yeah, okay. So some people are just telling me that they had to leave. So though that's some of the more natural and expected directions in which the study of the weaker base theory would go, and many of them were already sort of taking off in the 20th century and only continue in this one. But there are some new phenomena that emerged in the last, say, 20 or even fewer years that I wanted to mention before coming to a necessarily very short description of our own work. So, for example, these are just examples, right? These are small vignettes, samples of work that has been done. In a nice paper from 2009, Takako Nemoto showed an example of two statements about determinacy of games played in the Cantor space, and they're both known to be equivalent to weak Koenig's lemma, to WKL0, over the traditional base theory that had sigma 1 induction. And what she proved that if you weaken the base theory, one of them is equivalent just to weak Koenig's lemma, but the other one is stronger. It's equivalent to WKL0, meaning it's equivalent to a conjunction of weak Koenig's lemma and the sigma 1 induction. So this weakening of the base theory allows you to carry out a finer analysis, reverse mathematical analysis of some theorems, and to notice that some things, the equivalences between things that look the same from the point of view of the stronger theory, they're really not the same, because one of them really requires a use of a stronger induction axiom, which means more proof theoretic strength and so on and so on. Then, a bit more than 10 years ago, Keita had a nice simple paper where he made like the first step at analyzing principles from the zoo, from the point of view of reverse mathematics over RC 0 star, but also stronger Ramsey theoretic principles like this Ramsey for triples. That's equivalent over to AC 0 over the traditional base theory. And he proved that all these principles that he's considering, they're pi 2 conservative, at least over our base theory. So, for example, the provably total functions are only the elementary recursive functions, not all the primitive recursive ones, as in RCA0. As a consequence, this sort of shows that the difficulty that Simpson and Friedman mentioned, that Ramsey's theorem for triples implies AC0, that the proof seems to require the stronger base theory. It turns out to be an essential thing. So over the weaker theory, it's no longer equivalent to AC0. And eventually, I would highlight a sort of never published but influential preprint of David Belanger. Eventually, it turned out that studying reverse mathematics over this weaker base theory is actually useful in understanding some pretty challenging technical questions. Traditional mathematics over the stronger base theory. I will not get into that, but it turned out that it's not just like art for its own sake, but if you're okay with and interested in studying difficult questions of the more traditional kind of reverse mathematics, then it might make sense to learn and study the weaker base theory as well. So now that leaves you with, let's say, maybe up to 15 minutes to describe the work that we have been doing. And we here means mostly Keita, my student and postdoc, so Marta Fiori Carones was a postdoc from in Warsaw. Kasia Kowalik is my almost finished now PhD student. We also, on some aspects of this, but not specifically on statements from the zoo, we also work with Tin-Loc Wong, with Lawrence Wong from Singapore. He would appear on the references of the later slides. We decided to carry out a more systematic study of how such statements from the zoo behave in this weaker base theory. And once you want to do that, you must make an important conceptual distinction. So all of these principles say that for some kind of coloring of natural numbers, this coloring might correspond to some kind of ordering or it might not. There is an infinite set with some properties. So for example, let's just look at Ramsey's theorem for pairs in two colors. Ramsey's theorem tells you that for any coloring of pairs of natural numbers by two colors, there is an infinite homogeneous set. And you have the word infinite appearing in lots of other, in all of the other statements as well. So now, what does infinite mean? What does infinite subset of the natural numbers mean? That can have at least two meanings, and they will correspond to two different kinds of Ramsey theoretic principle. So we can say that, infinite homogeneous set means only unbounded in the natural numbers homogeneous set. We call that a normal principle. That's a name that the normal is because I think this is the proper notion of infinity in this weaker theory. And then there's a strong notion of infinity where you might want to require the homogeneous set to have the same cardinality of the natural as the natural numbers. So you might require a bijection between the homogeneous set and the entire universe of natural numbers. And the principle that tells you that, for every coloring, there is a set of cardinality of the natural numbers with a certain property, for example, homogeneity in the case of Ramsey. We call those long principles. And we studied both sorts of principle. I will try to say something very briefly about both cases, but in particular the normal ones. So In the study of the normal Ramsey theoretic principles, possibly unexpected tool appears, namely the theory of coded sets on cuts in the number theoretic universe, in the first order universe. So if you're given a model of, let's just say this, our base theory, RC is your star, and in that model you have a proper cut, then for that cut you can define the family of subsets of that cut that are coded in the model. That is exactly the traces of the sets from the second order, from the set theoretic universe on that cut, the intersections of the sets from the big model with the cut. And this object is interesting in that it does not really depend on the set theoretic universe. It turns out to depend only on the first order universe of the big model and on the cut. It doesn't depend on what exactly family of subsets of the big model you have in your structure. A particular special case of this is called the standard system of a model. So those are the coded subsets of the standard cut. The standard cut is the smallest cut in a possibly non-standard model of arithmetic. And you can talk about what subsets of the standard model are intersections of things that the big structure believes to be sets with the standard model. That's called the standard system. This structure of coded subsets of a cut can function as a sort of second order universe with the cut as the first order universe. And it's actually a pretty reasonable structure. It satisfies a non-trivial theory. Namely, if you take a cut which is closed under the exponential function, and in RC 0 star, if you don't have sigma 1 induction, there will always be a sigma 1 definable cut of that sort. Then the structure consisting of the cut as the first order universe and the coded sets, there's a missing parenthesis here, as the second order universe, it satisfies, well, our base theory RC 0 star, and in fact more. It also satisfies weak Koenig's lemma. So it satisfies a theory known as WK 0 star. The weaker base theory plus weak Koenig's lemma. So that's a meaningful theory. And our result that was proved with Marta and with Kasia, but it has a sort of antecedent in earlier work with Keita and Kasia, is that if you take any of these four Ramsey theoretical principles they described, and in fact, any principle from a much wider class that you can describe syntactically, then the following very weird thing happens. If you take one of these principles, this should be capital psi here, and you have a model of RC 0 star, and you have a proper sigma undefinable cut, then it turns out that the Ramsey theoretic principle is true in the big model if and only if it's true in the cut. So it is, you can reduce the truth of the Ramsey theoretic principle in the big model to truth in just a small piece of that model in the cut. So this is a pretty amazing at first sight, because if you look at this equivalence here, the left-hand side does not depend on the cut you choose. So this would be, if this Ramsey theoretic principle is true in one cut, it's going to be true in any other sigma 1 definable cut. On the other hand, the right-hand side, as mentioned, this family of sets that are coded on the cut does not depend on the set theoretic universe. It only depends on the first order universe. So as long as you have a fixed sigma 0 definable cut, it does not matter what second order universe you have. All the second order universes on our first order structure will either satisfy the principles, Ramsey theoretic principle, or they won't. Or all of them won't. So this is a pretty shocking at first observation. In some sense, it tells you that these normal Ramsey theoretic principles, they depend only in a very, very slight way on the second order structure of the model. They're almost like purely first order principles as soon as you don't have sigma 0, 1 induction. So failure of sigma 0, 1 induction, the existence of such a proper sigma 1 cut is a major thing. I will completely skip important coding lemma due to Chong and Morad, and like they've proved in the very early stages of reverse recursion theory. But this has some interesting consequences. So let me talk for at least 5 more minutes, and then I'll stop. So, for example, it turns out that all of these normal Ramsey theoretic principles, they are at least partially conservative over the base theory. In fact, they're pi03 conservative. On the other hand, they're almost never pi11 conservative. So almost always they will prove some new pi11, usually even a purely arithmetical statement that the base theory doesn't prove. If they are to be pi11 conservative, they have to follow from Weak-Koenig's lemma. And as mentioned already, most of these Ramsey theoretic principles from the zoo, they will not follow from Weak-Koenig's lemma. There's a very weird phenomenon also going on, such that it can happen that for a certain set, every computable coloring of pairs by 2 colors relative to that set, with that set as oracle, might have a computable in that set infinite homogeneous set. So this is something that is known to be false in the real world. This is like a very basic theorem of Specker. A really classical result. There is a computable coloring of pairs that has no computable infinite homogeneous set. So this can be proved. This result of Specker can be proved in RC0, but the proof breaks down in the weaker base theory in an essential way. It can really happen that all computable colorings will have computable homogeneous sets in a model of RC0 star. So that's we have a relatively good understanding of these normal principles over RC0 star. For the long versions, you have to make some distinctions again. So you can look, for example, at ADS, this principle that tells you that in any linear order defined, say, on the natural numbers, on an infinite linear order, there will either be an infinite ascending chain or an infinite descending chain. Now we want a long witness, so we want a witness of the size of the natural numbers, not like a small, sparse, unbounded witness. And you can formalize this infinite descending or ascending chain in at least 2 ways. You can either say that there is a subset of the natural numbers of full cardinalities, of cardinality of the natural numbers, such that on this subset, either the ordering always agrees with the usual ordering, so that's an ascending chain, or the ordering always disagrees with the usual ordering, so that's a descending chain. Or you can simply say that there's a sequence, there's a function indexed by the natural numbers, which is either strictly increasing or strictly decreasing with respect to your ordering. We call the first version of long ADS the set version, and we call the second version of the sequence version. And it turns out that they're not at all similar in strength now over RC0 star. Namely, the set version actually implies the traditional base theory. So it implies sigma 0, 1 induction. And this is by adapting to the setting of ADS and by Keita for this long version of Ramsey's theorem. And it also works for the long version of the chain anti-chain principle. So Ramsey for pairs, chain anti-chain, and the set version of ADS set, if you take their long versions, they actually imply the older, stronger base theory. On the other hand, the sequence version of long ADS turns out to be equivalent to this normal ADS, which is content with any unbounded increasing or decreasing sequence, even a very, very sparse one indexed by a very, very small proper cut. Again, I have to skip the proofs. So in the end, the story that you have is that many of these long principles disappear in the sense that they already give you the old base theory. This is true for RT22, this is true for chain anti-chain, this is true for ADS. Whereas the normal principles, they're all much weaker. They are equivalent, they are all pi03 conservative over the weaker base theory, so they're nowhere close to the stronger one. In particular, they don't prove the existence, the totality of non-elementary recursive functions. And you more or less get a similar sequence of implications as you did over RC0 for these normal versions, except note that we don't know the problem whether the ascending descending sequence principle implies the cohesive Ramsey's theorem. And also, the long version of cohesive Ramsey turns out to be weak as well, but the equivalence between the two principles uses weak Koenig's lemma. So it follows from some conservativity results. This is also pi3 conservative over the weaker base theory, but we don't know if it's equivalent to the normal version of cohesive Ramsey. Okay, 3 things that I'll mention at a pace of half a minute per slide, I guess. So firstly, Ramsey for triples, and longer tuples. That tells you if you color, say, triples or longer n tuples of natural numbers by 2 colors, then there will be an infinite homogeneous set. We have a full, as mentioned, that implies AC0 over the stronger base theory over RC0, but that proof, which I have to skip in the interest of time, really requires sigma 1 induction. And it turns out that the same characterization in terms of cuts applies to Ramsey for triples, for quadruples, and so on, as for the principles from the zoo. And therefore, we get pi3 conservativity over RC0 star. Moreover, in this case, this is a result by Keita, Kasia Kowalik, and myself. We can give a full axiomatization of the first order consequences of, say, Ramsey for triples over the weaker base theory. And this is a very weird fragment of piano arithmetic that is not full piano arithmetic. It's strictly weaker, but it's not finitely axiomatizable. And for example, for every k, it tells you that sigma k induction implies delta k plus 1 induction. So that's like an interesting and strange phenomenon happening here. Secondly, another way, I was really hoping that I would get to this, but I sort of ran out of time faster than expected, because this has Gödelian aspects to it, and I know that Young is interested in Gödel's theorem very much. So we have various results on proof sizes, on proof speed up, that, for example, show that over the weaker base theory, Ramsey for pairs has iterated exponential speed up of proofs, even for like very simple sentences, namely finite consistency statements. And this is highly connected to things like the finitistic Gödel's theorem, quantitative versions of reflection principles, and so on. Interestingly, Ramsey for pairs does not have speed up over the stronger base theory, at least for pi3 sentences. And over the weaker base theory, the chain anti-chain principle doesn't have speed up either. This is a recent, still not completely published result. I mean, it's still not public, I think, but there is some sort of preprint due to Kasia Kowalik. So this is really, another way of distinguishing between the strength of theorems. Do they give speed up or not over the weaker base theory? And finally, our probably deepest result by Marta Fiori-Carones, Tin-Lock Wong or Lawrence Wong, Keita, and myself, is that there's a sort of quantifier elimination result for weak Königs lemma, or second order quantifier elimination, result for weak Königs lemma in the presence of explicitly negated sigma 1 induction. So, for example, one consequence of this, and this is just one consequence, is that if you have a principle, a pi 1 2 sentence that's pi 1 1 conservative over the weaker theory, over the weaker base theory, then weak Königs lemma, if you explicitly negate this induction, it will prove this principle. So in the setting where you have the weaker base theory, but you don't have sigma 1 induction, weak Königs lemma is the strictly strongest pi 1 1 conservative principle. And that's a phenomenon that doesn't have any analog in the traditional reverse mathematics. And it also matters for the study of some problems in traditional reverse mathematics. So this, I think, is probably the most significant discovery that we have made. There are a number of open problems, and maybe I'll leave this slide. I also have some sort of bibliography giving a sample of papers that appeared here, but maybe I will stop and say thank you very much on this open problems slide. Thanks.